Okay, three-phase Y connection, Y to Y. The Y to Y looks bizarre. What does that mean, Y to Y?
They're connected.
That's Y source connected to Y load. So both are Ys. The source is a Y, the load is a Y. We talked about in the previous lectures, not the one just before this, but before that, we talked about a three-phase system. And a Y-connected three-phase system will look like this. I draw them looking like the letter Y. Notice the bottom one, the minus is always toward N. This is N, this is A, this is B, and this is C. Now, sometimes you hear the book talks about positive ABC three-phase system or negative. Let's talk about positive versus negative. When the book says positive, ABC source, ABC Y connected source. That means if VAN equals some peak value or RMS value, it doesn't really matter, angle 0, then VBN will be same value, same magnitude, but the angle will be negative 120, and VCN will be VP angle negative 240. So when you hear the word positive, when you hear negative, sometimes in the problem they said positive or negative. Negative ABC Y connected source, then VAN will be VP angle 0, VBN will be what? VP angle 120, and VCN will be VP angle what? 240. Now, when you think about this, like, why not just call this negative because these are negative and call that positive because these are positive? Why not? Doesn't that make sense? So when it's a positive source, these are negative. When it's a negative, these are positive. Well, the reason they call them positive, when you have a negative 120, where do you start? Remember the shifting in math? You start 120 degrees where? On the right side. So for this one, if VAN looks like this, then VBN, since it started negative 120, a negative 120 is actually a phase shift in the positive X direction. And VCN will be 240, and 240 is somewhere here. So notice they're all starting where? On the positive side of the x-axis.
That makes sense in terms of lagging or leading.
Yep, true. And now with negative, so this is the positive here. And there's the negative. This is VAN. Uh-oh. I screw up here. So VBN will be where now? Right here. and VCN will be right here. So notice you're starting right on this end for negative.
Is there any reason for the subscript P next to the V for each of those values?
Oh, that's the peak value.
P, okay.
Yep. So if this like 120 here, maximum or peak value, so that's what that number, like if it's a sine wave, it would be 110 in the US, that'll be 110 angle 0, 110, 120, 110, 240, the peak value. So that's the first thing about Y to Y, positive phase sequence, ABC, negative phase sequence, positive phase sequence. So make sure when you look at the problem, you know what they're talking about. The one we deal with most of the time is positive sequence. You'll see most of the problems in the book, we're dealing with positive sequence, not a negative sequence. Now, if I want to find the voltage in A and B here, so I'll use the positive sequence. Let's take that. I wasn't sure if I was recording.
You were.
I want to make sure. Again, I'm using positive sequence, so this is VP angle 0. This is VP angle what? Negative 120. This is VP angle negative 240. If I want to find VAB, quick reminder, what's VAB? Well, that's plus here, minus there. So if you take a meter and you attach it right there, M4 meter, plus on this end, minus on that end, what are you going to see? It's going to be VAN minus this voltage, which is VBN. So this is labeled as VAN, this is labeled as VBN, and this is labeled as VCN. You can actually see it better if I was doing A to C. If I was doing A to C, it's plus to minus, minus to plus. The same thing, plus to minus, minus to plus. So it has to be subtractions. So that's going to be VP angle 0 minus VP angle negative 120. And if you do the math, you can factor out a VP out. 1 angle 0 minus 1 angle negative 120. I'll do the math just to show you here. 1 angle 0 minus 1 angle negative 120 is at 1.7. 1.732, what's the angle? 30. What is the 1.732? That is the square root of 3. So what you're going to find out that VAB is going to be the square root of 3 times the peak voltage, and whatever this angle here, you add 30 degrees to it. Since it was 0, that would be 30 degrees. And if you have a balanced source, what does that mean, balanced source? That means these values are the same. VP, VP, VP. The phase shift is 0, negative 120, negative 240. You're in good shape because that means you know what VBC, the voltage in B and C, is going to be the same as this one. And now take this angle and subtract from it 120. So when you subtract 120, what are you going to have for a value? It's negative 90 degrees. I'm going AB, BC, now CA. Notice I'm going this way. AB, BC, then CA. So VCA is going to be the square root 3 times VP, the angle 30 minus 240. That's what's nice about a balanced source. Once you know one, you know the rest of them. We call this value V line, VL, which is the square root 3 times VP. Why we call it VL? That's known as line-to-line voltage. So if they say the line voltage, they're talking about VAB. If they say the phase voltage, we're talking about VAN. And the problem sometimes trying to get you confused.
Wait, so you said that this is supposed to be a balanced source.
Yes,
How come the phase shifts are kind of like off?
they're still 120 degrees off each other.
Are they?
Yep.
Oh,
30,
positive, okay.
negative 120, negative 210.
I was looking at that.
Now let's take an example that has a Y to Y connection. We'll go through the math, we'll find all the answers for it. Let's take a Y source connected to a Y load. Everyone's all set with this one? Here's an example. I have a Y source, and the value is 200 angle 0 volts RMS. This is N. This is B here, balanced source. This is C. And it's connected to a balanced load, which has a resistor and an inductor. Resistor and an inductor. Notice I use capital C, capital A, and capital B. And let's assume each one of, yeah,
The order of the
resistor, capacitor, no,
inductor?
no.
Okay.
100 angle 60. This is capital N. So the way we connect this is A, B, and C. A is connected to A. Like this. B is connected to B. N is connected to N. And C is connected to C. That is a balanced source connected to a balanced load. Okay. The question here, find the current, find the line current. So the line current is what? I from little a to big A. I from little b to big B. And I from small c to capital C. Second question. Find the line voltage. What does that mean? That's V, AB, V, BC, and VCA. And maybe the last question, find, I don't know, the average power absorbed by each phase. Sounds like a lot of questions. But if you trace one of these, maybe I can get... The nice thing about Y to Y, if you trace one of them, one path, notice this is one path. The same current going through them, it doesn't split. So the current going through this source is the same current going through that load, isn't it? There's no other way to split. Once it leaves that source, has no other way to go till it gets to the ground. This is the ground here, the neutral point. So the current through this one is the same current through A to A, is the same current through that load there. So what we do with these normally, we just look at one phase. So let's take a picture of one phase. Let's take the top and let's go through it and find what that current is. And if I know what that current is, I can tell you what the voltage VAB, I don't have to do any math to it. Minimal math. So looking at one phase, this is what I see. I see VAN here, which happens to be what? 200 angle 0 volt RMS. This is A. This is N. It's going through a resistor and an inductor. This is capital A. This is capital N. And the value for this is what? 100 angle 60. Can I find the current now? Can I find the current from A to A? Isn't that just Ohm's law? 200 angle 0 divided by what? 100 angle 60. 2 angle negative 60 degrees. Here's the good news. Since I have a balanced source, that's a balanced source with a balanced load, I know what the other two currents. I know what I from B to B is going to be the same except the phase shift. Subtract from it another 120. And I know the current from C to C. Subtract from the negative 60, what, 240? So I answered the first three questions. What is I sub A, B, B, and C, C? I also know that VAN happens to be what? 200 angle 0 volt RMS, right? What is VBN? That was a positive source here. VBN will be what? 200 angle negative 120. And VCN is going to be what? 200 angle negative 240. So if they ask for the phase voltages, these are the phase voltages. Can I tell you what VAB is now? We just derived that equation. We said VAB is going to be the square root of 3 times the peak voltage, add to it 30 degrees. So what is the square root of 3 times 200? Add to this voltage, add to this angle 30 degrees. Whatever that number here, whatever that angle, add 30 degrees to it. My calculator here is a 346. Angle 30 degrees. I know now what VBC. It's going to be the same number, subtract 120 from it. I can tell you what VCA. It's the same number, subtract 240. Now, if this was not balanced source, you really couldn't say that. You have to say that VAB equals VAN minus VBN. VBC, it's VBN minus VCN. VCA equals VCN minus VAN, if it wasn't balanced. When it's balanced, once you know the first one, subtract 120, subtract another 120. Done. But you will encounter some problems where they're not balanced. So if they're not balanced, I'll give you here. If they are not balanced, you got to do VAN minus VBN. If it's not balanced, you have to do VBN minus VCN. That's an N. This will be VCN minus VAN. So you have to go and do the math for each one. If they're not balanced, you can't guess what these are. They have to give you these values, which means these currents will not be the same. You got to do 3 separate circuits, one for each one of these, because this is VAN divided by that impedance. For the next one is going to be VBN, and if it's different, the math is going to be different. And the last one, can we figure what the average power delivered to this one? Well, I know the current. So let's do it. What is the average power delivered to AN? Well, we know is what? VRMS, IRMS, cosine theta V minus theta I. The voltage here is what? It's 200 in parallel. The current through AN is the current through AA. It's the same current. There's no other way to exit. Cosine theta V, what's theta V? 0 minus what's theta I? Negative 60, so plus 60. $200 times 2 times cosine 60. It is 200 watts. What do you think the average power absorbed by BN and CN? 200 watts. So if you want the total power, total average power, total average power delivered to the load will be 3 times, we have a 3-phase, 3 times 200, which is 600 watts. You have 3 of them. 3 sets of them.
Is A, B, C?
Yeah. If you redraw this one, you have another one. BN, going through that. CN is this one. You got 3 sets of these. So that's why you got actually 3 times that number. Where this becomes really not fun, or I should say not fun, a little bit challenging. Now when this is Y and that's delta, or this is delta and that's Y, it's not as straightforward.
Well, you just turn delta into Y, right?
I got to turn one to the other. I can then turn delta to Y or Y to delta. And that's what we're going to do next class. You have a Y source with a delta load. And you have to convert that delta load to a Y load and just apply these rules.